Limits. Well, we might have to find the limiting values of functions like this one here. As x tends to 0, we might have to find the limit of that function as x tends to infinity. And some of these are more straightforward than others, and we'll look at how to do that and the rules around limits. And sometimes we get these nasty functions here. I'm finding the limit as x tends to 0 of the sine of 0, which is 0 divided by 0. So how am I going to deal with that? Well, we've got our trusty Taylor series to help us with that. Okay, so let's get our principles right in this first video. What am I writing here? Well, it says I'm trying to find the limit, shorthand lim, as the value of x tends to, the arrow is tends to a, which is some value. And I'm finding the limit of this function here. Okay, so here's my graph, here's my function. If I find a value of around a, I'm working at x equals a. So what I'm doing is starting at some point near a, finding its value of the function, that's f of x up here, isn't it? And then as I move towards a, as I get closer and closer and closer and finally arrive at a, well, what's the value of the function going to be? Well, if it exists, the value is going to be f of a, isn't it? So it is important it exists. So you quite often see as an extension of what we've written here at the top, what I've written below, which says if f exists at x equals a, then the limit of the function f of x as x tends to a is of course f of a. Now some of you will think that this is what I call in my generation stating the bleeding obvious, but it's quite important piece of mathematics, and for purity we need to be clear about it. It also has a bunch of corollary laws that will be helpful. So that's the expression we just wrote, isn't it? That the limit of the function f of x as x tends to a is f of a. And of course, if I just took my function and multiplied it by some constant k, then the limit of k f of x as x tends to a is going to be k lots of f of a. Pretty straightforward, eh? Also true then is if I've got two functions and these functions exist at x equals a, they've got to have a value, that the multiple of the product of f of x multiplied by g of x, the limit of that as x tends to a, is just going to be f of a times g of a. And that was a product. Let's look at a quotient, a fraction, an algebraic fraction. So what's the limit of f of x divided by g of x as x tends to a? Well, that's just going to be the value of f of a divided by the value of g of a. Okay, all stating the bleeding obvious, but you're all sat there going, so how am I going to use that? Let's have a look. Right, let's find what the value of this function here is, this overall function, as x tends to 0. Now some of you will look at that and think you know the answer, which is minus 6/7, but let's work it out mathematically and prove it. So I'm going to say that the top function here, the numerator, is going to be f of x, and my denominator is going to be g of x. Yeah, so there it is there. So f of x is going to be 2 plus x. And what's that value going to be as when x equals 0? Well, it's just going to be 2 times 0 plus 6, so it's going to be plus 6, isn't it? And if we look at the denominator, well, g of x is x minus 7, and what's going to be g of 0? When g and x equals 0, it's just going to be minus 7. Now, using the rule that we just worked out, we can see that if I want to find this limit here, all I have to do is f of a over g of a, which is f of 0 over g of 0 in this case, which is plus 6 over minus 7, which is minus 6/7, isn't it? So therefore, what is the limit of this as x tends to 0? Well, it's 6/7. Not too difficult, eh? Now we can use this method as well for any value of a. Any value of x, yeah, a is any value of x. So what happens as x tends to infinity here? Let's have a look. of exactly the same function. Now, some of you will look at that and go, well, that's infinity over infinity. You might think that's 1. Some of you might think that's 2 lots of infinity divided by infinity plus something very small. So I ignore the little bit that's very small. And you might have already worked out that the limit's going to be 2. But what we want to do is to be more precise mathematically, and this is what the examiner is going to expect you to do. So how am I going to fix the problem that I've got up here? I don't want to have an infinity over infinity. That's no use to me. I want something that's finite. So if I look at the top, well, that's a multiple of x, isn't it? And the bottom's a multiple of x. So if I divided the top and the bottom by x, what would I get? Well, my top would become 2 plus 6 over x, wouldn't it? And that's my numerator, and my denominator will become 1 minus 7 over x, yeah? There we go. What's going to happen to that? Oh, that's an x there. They're going to become finite values as x tends to infinity now, isn't it? I'm not going to get an infinity over infinity. Okay, so if I do that, which is what I've done here, I define the top as being f of x. That's going to be 2 over 6x. There we go. What am I interested in? Well, I'm interested in what the value of that is as x tends to infinity. Well, 6 over infinity tends to 0, doesn't it? So the second term effectively tends to 0, and I'm just left with this. So f of infinity of in my revised numerator is plus 2, isn't it? What happens in my denominator? Well, I've got g of x is 1 minus 7 over x. X tends to infinity, so the second term tends to 0 again. So I'm just left with the first term, aren't I? Which is 1. So substitute those into my formula now, and a is infinity, so I've got f of infinity over g of infinity. I've got plus 2 divided by plus 1. 2 over 1 is 1. So what's the limit as x tends to infinity of this function here? Well, it's 2. There we have it. That's how we use it. So here's something you could stop the video and take down, take a note of. But that's our basic idea. Here's the terminology. Here's the basic rules we're going to use. The product tends to be more straightforward than the quotient one because we can get this 0 over 0 malarkey, which we need to sort out. And if you've got one of those infinity over infinities, remember we need to get rid of infinity over infinities by redefining our function. That's our functions there. And what I did is I divided by x top and bottom, didn't I? So that they both become finite. And there you have it, part 1.